everything you see around you will end. Not in some distant, abstract way, but completely and permanently. The stars will burn out. Galaxies will drift into darkness. Even the atoms that make up your body will eventually cease to exist. And the universe? It faces a death so absolute that time itself becomes meaningless. Right now, in 1998, two teams of astronomers are staring at their data in disbelief. They've been studying distant supernovae, stellar explosions so bright they can outshine entire galaxies. What they've discovered will win them the Nobel Prize and fundamentally change our understanding of reality. These dying stars are dimmer than they should be, farther away than expected. The universe isn't just expanding, it's accelerating. Something is pushing the cosmos apart faster and faster, and we have no idea what it is. This invisible force constitutes 68% of everything that exists. We call it dark energy, though that name reveals how little we understand. Dark matter and ordinary matter, all the stuff we can actually see and touch, make up just 32%. Your body, Earth, the Sun, every galaxy we've ever observed, all of it is a cosmic minority. The vast majority of the universe is something else entirely, something we can't detect except through its effect on space itself. And this mysterious force will determine how everything dies. The universe has been expanding since the Big Bang 13.8 billion years ago. For most of that time, scientists assumed gravity would eventually slow that expansion, maybe even reverse it. Like throwing a ball in the air, it should go up, slow down, and fall back. But that's not what's happening. The ball is accelerating upward, defying every intuitive understanding of how reality should work. Dark energy changes everything. It doesn't just mean the universe will expand forever. It means the expansion itself will become more violent over time. Space between galaxies is growing. That distance will increase faster and faster until something breaks. What breaks depends on the nature of dark energy itself, and we have several terrifying possibilities. The most likely scenario is called the Big Freeze, or heat death. Temperature isn't what you think it is. It's really about energy differences. Hot coffee cools down because heat flows from high temperature to low temperature, from the coffee to the air around it. Work, in the physics sense, requires these differences. Your car engine works because fuel burns hot and exhaust leaves cold. Your body works because chemical reactions create temperature gradients. Life itself depends on energy flowing from one place to another. Heat death means the end of all differences. The second law of thermodynamics states that entropy, the measure of disorder, always increases in an isolated system. The universe is the ultimate isolated system. There's nothing outside it. No energy coming in. No heat leaving. And entropy has been increasing since the beginning, spreading energy out, smoothing over differences, making everything more uniform. Eventually, this process completes. Every region of space reaches the same temperature. Energy distributes perfectly evenly across the cosmos. And when that happens, nothing can happen anymore. No stars can form. No reactions can occur. No thoughts can be thought. The universe reaches maximum entropy, a state of absolute equilibrium where time continues but change stops. This isn't some theoretical possibility we can dismiss. It's the most probable outcome based on everything we currently observe. The evidence points toward eternal expansion, endless cooling, and ultimate stillness. The heat death theory represents perhaps the most sobering conclusion ever drawn from scientific inquiry. Not just a hypothesis about stars and galaxies, but a fundamental statement about the destiny of everything that has ever existed or ever will exist. But when does this happen? The timeline stretches across numbers that strain human comprehension. Right now, we're in what might be called the golden age of the universe. Star formation peaked billions of years ago, but new stars still ignite regularly. Galaxies still collide and merge. Black holes still consume matter. The cosmos remains dynamic and active. That won't last. Star formation requires gas, primarily hydrogen, compressed by gravity until nuclear fusion begins. The universe contains a finite amount of this raw material. As stars form and die, they convert hydrogen into heavier elements. Some of that material gets recycled into new stars, but much of it becomes locked away in stellar remnants, white dwarfs, neutron stars, black holes. The available supply steadily decreases. In about 100 trillion years, the last conventional stars will form. That sounds impossibly distant, but it's just the beginning. Low-mass red dwarfs, the most common type of star, burn their fuel incredibly slowly. The smallest can survive for over 10 trillion years. These dim members will be the last natural lights in the universe, slowly fading over timescales that dwarf all of recorded history by factors of millions. And when those final red dwarfs exhaust their fuel, the universe enters the degenerate era. Only stellar remnants remain. White dwarfs, the dense cores of dead stars, slowly cooling in the darkness. Neutron stars, objects so dense a teaspoon would weigh as much as a mountain. Black holes, regions where gravity has crushed matter into singularities. These aren't temporary states. They're stable configurations that could persist for incomprehensible stretches of time. Except they don't persist forever. Even these seem permanent objects face dissolution. The mechanism involves something most people have never heard of: proton decay. Protons are the particles in atomic nuclei, and conventional physics treats them as stable. An atom of hydrogen, one proton and one electron, should last forever. But some advanced theories suggest protons aren't actually immortal. They might decay into lighter particles with a half-life somewhere between 10 to the 31st and 10 to the 36th years. We've never observed this happening. The current experimental limit puts the proton lifetime at least 10 to the 29th years, and it might be far longer. But if protons do decay, the implications transform our understanding of matter's permanence. Wait long enough, about 300 times the proton half-life, and all ordinary matter breaks down. Every atom in every dead star, every particle drifting through space, all of it decays into radiation. White dwarfs, those dense stellar remnants. They're mostly carbon and oxygen, elements built from protons and neutrons. If protons decay, white dwarfs gradually dissolve, particle by particle, over timescales measured in 10 to the 40 years. Neutron stars, even denser objects made almost entirely of neutrons. Neutrons outside atomic nuclei are unstable anyway, decaying in about 15 minutes. Bound inside neutron stars they're stable, but if proton decay occurs through the mechanisms predicted by grand unified theories, neutrons decay too. The entire neutron star slowly evaporates into space. This isn't destruction through violence or collision. It's dissolution through quantum decay, matter simply ceasing to be matter, transforming into massless particles that spread through an ever-expanding void. And when this process completes, when all the ordinary matter has decayed away, only one type of object remains dominant in the universe. Black holes. These gravitational monsters will be the last complex structures, the final holdouts against entropy's relentless march. And they won't last either. Stephen Hawking discovered that black holes aren't actually black. They emit radiation through a quantum mechanical process now called Hawking radiation. Virtual particle pairs constantly pop into existence throughout space, matter and antimatter appearing and annihilating in fractions of a second. Near a black hole's event horizon, one particle can fall in while its partner escapes. The escaping particle becomes real radiation, and that radiation carries away energy. The black hole loses mass. For stellar mass black holes, this process is incredibly slow. A black hole with the mass of our Sun would take roughly 2 × 10⁻⁴ years to evaporate completely. That's a 1 followed by 64 zeros. The universe is currently only 1.4 × 10⁻⁻⁻ years old. We're not even close to the timescale where Hawking radiation matters. But wait longer. Much longer. And even supermassive black holes, the giants at galaxy centers with masses billions of times our Sun, eventually evaporate. A black hole with 10 billion solar masses takes about 2 × 10⁻93 years to disappear. The largest black holes, which might grow to 100 trillion solar masses as galaxy clusters collapse, could persist until 10⁻110 years. Then they're gone. Every black hole evaporates. Every particle of ordinary matter has decayed. The universe becomes a thin soup of photons and other massless particles, spreading ever farther apart as space continues expanding. Temperature approaches, but never quite reaches, absolute zero. And here's the truly unsettling part: this condition persists forever. The dark era begins. No stars exist. No planets orbit. No structures of any kind remain. Just isolated particles drifting through a space so vast that the distance between any two particles exceeds the size of the observable universe today. Time continues, but nothing happens. Nothing can happen. All the energy that once powered stars and galaxies and life has been distributed so evenly that no gradients remain to drive any process whatsoever. This is heat death. Not an explosion or a crunch, but a fade-out. The universe doesn't end with violence but with silence. And unlike other cosmic catastrophes, heat death offers no escape. It's not a local phenomenon you might avoid by moving somewhere else. It's the final state of the entire cosmos, the ultimate equilibrium from which nothing can deviate. Human civilization exists in a narrow window, a brief moment between the Big Bang and heat death when stars still shine and complexity remains possible. We look up at a sky full of galaxies, but that view itself is temporary. In about 100 million years, the accelerating expansion will have pushed distant galaxies beyond our cosmic horizon. Future observers won't be able to see them at all. The universe will appear much emptier than it does today, and we're already seeing it after most of the action has passed. But heat death isn't the only possibility. Dark energy might not behave the way we think. Its influence might change over time, strengthening or weakening in ways we can't yet predict. And if it strengthens, if the repulsive force pushing space apart grows more powerful, something far more violent awaits. The Big Rip doesn't wait for trillions of years. It operates on a completely different timescale, measured in mere billions. 22 billion years from now, according to some calculations, though that estimate carries enormous uncertainty. The mechanism is straightforward but devastating. Dark energy, the mysterious force driving cosmic acceleration, might not remain constant. If it strengthens over time, if the repulsive effect pushing space apart grows more powerful, then expansion accelerates without limit. Space itself becomes the weapon. First, galaxy clusters tear apart. These are the largest gravitationally bound structures in the universe, held together by dark matter and the combined gravity of hundreds or thousands of galaxies. When expansion overcomes that binding force, clusters dissolve. Galaxies drift away from each other, and the cosmic web that gives the universe its large-scale structure simply unravels. This happens roughly 1 billion years before the final rip. Then individual galaxies shred. The Milky Way, Andromeda, every spiral and elliptical galaxy in the cosmos, torn apart as space expands faster than gravity can hold stars in orbit. Stars scatter into the void. This occurs about 60 million years before the end. 3 months before the Big Rip, solar systems disintegrate. Earth tears away from the Sun. Jupiter drifts off into darkness. Every planet in every system across the universe suddenly becomes a rogue world, untethered and alone. But there's no time to adjust to this new reality. 30 minutes before the end, planets themselves come apart. The expansion of space overwhelms the electromagnetic forces holding molecules together. Rock and metal and ice simply separate into their constituent atoms. Earth doesn't explode. It dissolves, pulled apart at the molecular level by expanding space. The final second is reserved for atoms. Electrons rip away from nuclei. Protons and neutrons split apart. Even quarks, the fundamental building blocks of matter, separate. Space expands so violently that nothing can remain bound together at any scale. The universe becomes a sea of isolated fundamental particles, each one completely alone in a space expanding faster than light itself. Then what? The Big Rip scenarios don't typically continue beyond that point. Some models suggest spacetime itself tears apart, creating a singularity similar to the Big Bang but in reverse. Others propose that the fabric of reality simply fragments into disconnected regions where the laws of physics no longer apply in any recognizable way. We enter pure speculation because we have no framework for understanding physics after spacetime itself has been destroyed. But here's the critical question: is the Big Rip actually possible? Does dark energy behave this way? The answer depends on something called the equation of state for dark energy, represented by the letter W. If W equals -1, dark energy remains constant, and we get heat death. If W is less than -1, dark energy strengthens over time, leading to the Big Rip. If W is greater than -1, dark energy weakens, potentially allowing gravity to eventually dominate. Current observations from Type Ia supernovae, the cosmic microwave background, and large-scale structure surveys all suggest WEST is very close to -1. The best measurements indicate W equals -1.03, plus or minus about 0.06. That error range is crucial. It's large enough that we can't completely rule out W being less than -1. The Big Rip remains possible, though most cosmologists consider it unlikely based on present evidence. Recent data from the Dark Energy Spectroscopic Instrument adds an intriguing twist. DESI's observations suggest dark energy might not be constant at all. The data hints that dark energy was stronger in the past and has weakened over cosmic time. If this trend continues, if dark energy keeps weakening, we might eventually face a completely different fate. The Big Crunch. Imagine the universe's expansion slowing down, not because of the Big Rip but because dark energy fades away entirely. Gravity, which has been fighting a losing battle against expansion for billions of years, finally wins. The universe stops expanding and begins contracting. Galaxies that were moving apart start moving together. The cosmic microwave background, which has been cooling since the Big Bang, begins heating up again as space shrinks. This is the Big Crunch, a scenario that's almost the exact opposite of the Big Bang. As contraction accelerates, distant galaxies appear blue-shifted instead of red-shifted. Their light compresses to shorter wavelengths as they rush toward us. Galaxy collisions, which are rare in our expanding universe, become common. Stars merge. Gas clouds compress and ignite in massive bursts of star formation. The universe brightens. But this brightness is temporary. As space continues shrinking, temperatures climb. The cosmic microwave background shifts from microwave to infrared to visible light to ultraviolet and beyond. Eventually, the radiation becomes so intense it tears apart molecules, then atoms. Stars evaporate. Planets vaporize. All structure dissolves in the heat. In the final moments, everything collapses into a singularity. All matter and energy in the universe compresses into an infinitely dense, infinitely hot point. Time itself might end, or perhaps it continues through to the other side, triggering a new Big Bang and starting the cycle over. This is the oscillating universe model, where Big Bangs and Big Crunches follow each other in eternal succession. The oscillating universe sounds almost hopeful compared to heat death or the Big Rip. At least something new emerges. At least the universe doesn't just fade away or tear itself apart. But there's a problem, and it's a fundamental one rooted in thermodynamics. Entropy increases. That's not just a tendency or a guideline. It's a law. Each cycle of expansion and contraction must start with higher entropy than the previous one. Eventually, entropy reaches maximum, and no further cycles can occur. The universe ends in heat death anyway, just after a series of bounces. Roger Penrose proposed a fascinating solution to this entropy problem. His conformal cyclic cosmology suggests that when the universe reaches heat death, when all massive particles have decayed and only massless photons remain, something remarkable happens. The distinction between a very old, very large universe and a very young, very small universe becomes mathematically equivalent. Scale doesn't matter when nothing massive exists to provide reference. The end of one aeon smoothly transitions into the beginning of the next. No singularity. No violation of entropy. Just an endless series of cosmic cycles, each one stretching for incomprehensible spans of time. The evidence for Penrose's model is debated. He claims to have found circular patterns in the cosmic microwave background that represent gravitational waves from black hole collisions in previous eons. Other researchers dispute these findings, attributing the patterns to statistical noise. The theory remains speculative but not impossible. What if dark energy does something completely unexpected? What if it doesn't remain constant, doesn't strengthen, doesn't weaken, but oscillates? Periods of acceleration followed by periods of deceleration, creating a universe that expands and contracts in waves rather than monotonically. Or what if dark energy is not a fundamental property of space but a temporary phase, like water freezing into ice? Perhaps the vacuum of space can exist in different states, and our current state, with its accelerating expansion, will eventually transition to something else entirely. These scenarios push us to the edge of theoretical physics. We're forced to confront how little we actually understand about the universe's fundamental nature. Dark energy makes up 68% of everything that exists, and we don't know what it is. We've given it a name, measured its effects, constrained its properties. But we don't understand it. And without that understanding, predicting the universe's ultimate fate remains educated guesswork based on current observations that might not capture the full picture. Consider this: humanity has only been observing the universe scientifically for a few centuries. We've had detailed cosmological data for less than a century. We discovered dark energy in 1998. That's barely 25 years ago. Our entire understanding of cosmic acceleration, of the universe's fate, of everything we've discussed, rests on observations spanning less than one human lifetime. We're extrapolating from an infinitesimally small sample of cosmic history and declaring we understand how everything ends. The universe is 13.8 billion years old. We've been watching it carefully for perhaps 100 years. That's 1 part in 138 million of its total history. Imagine trying to predict someone's entire life story after watching them for a single second. That's essentially what cosmology attempts. We observe the universe for an instant and project forward trillions or googolls of years, confident in our models, aware of our ignorance, hoping the patterns we've identified remain valid far beyond the timescales we can verify. And yet, the mathematics works. The predictions align with observations. General relativity, quantum mechanics, thermodynamics, these frameworks have proven remarkably reliable. When we point our telescopes at distant galaxies, we see what the equations predict. When we measure the cosmic microwave background, the numbers match our models. The universe appears to follow rules, and those rules, when extended forward, lead inevitably to one of the fates we've described. So we proceed, building our models on foundations we can test today, hoping they remain valid across timescales that make geological epochs look like eye blinks. The Big Freeze scenario, our most likely fate, unfolds in stages. Each stage stretches longer than the one before. Each transition marks another threshold crossed, another form of order surrendered to entropy's relentless advance. First, the stars die. Not all at once. Gradually. Star formation peaks, then declines. We've already passed that peak, actually. The universe has been making fewer new stars for billions of years. The supply of hydrogen gas, the raw material for stellar birth, gets consumed or dispersed. Galaxies exhaust their reserves. New stars become rarer, then stop forming entirely. This happens within 1 to 100 trillion years. A massive range, but cosmologically, it's a blink. After that point, no new stars. The universe must survive on what it has. And what it has slowly burns out. Small red dwarf stars, the most economical burners in the cosmos, can shine for 10 trillion years or more. They sip their hydrogen fuel carefully, converting it to helium at rates so slow they outlast everything else. But even red dwarfs have limits. Eventually, the last one flickers and fades. The degenerate era begins. In this epoch, stellar remnants dominate. White dwarfs, neutron stars, black holes. No active fusion. No light from nuclear fire. Just the slow cooling of compressed matter and the gravitational dance of dead stellar cores. The universe doesn't go dark immediately. White dwarfs radiate stored heat for trillions of years, cooling from white-hot to red to brown to black. They're called black dwarfs in this final state, though none exist yet. The universe isn't old enough. Brown dwarfs form from gas clouds too small to ignite fusion. They glow dimly from gravitational compression and residual heat. In the degenerate era, they're everywhere. Cool, dark, slowly radiating their remaining thermal energy into the void. Galaxies persist during this time, held together by gravity. But they're graveyards. No spirals of blue young stars, no nebulae giving birth to new systems. Just the slow orbital decay of dead stellar remnants, occasionally colliding, merging, falling into central supermassive black holes. This process takes 100 quintillion years. one followed by 20 zeros. Most stellar remnants eventually get captured by the supermassive black holes at galactic centers. The rest get ejected through gravitational interactions, flung into intergalactic space to wander alone. And what about planets? Earth won't make it to the degenerate era. 5 billion years from now, the Sun expands into a red giant. It swells beyond Mercury's orbit, then Venus. Earth might be engulfed directly or might survive at the edge of the expanding photosphere, atmosphere stripped, oceans boiled away, surface molten. Either way, unrecognizable. 2 billion years after that, the Sun sheds its outer layers, leaving behind a white dwarf. Whatever remains of Earth orbits a fading ember. But let's say a planet somehow survives into the deep future. Rocky worlds orbiting dead stars. What happens to them? They don't last. Even solid matter isn't permanent. Here's where things get strange. Protons, the building blocks of atomic nuclei, might decay. We've never observed this. Experiments have looked for decades. Massive underground detectors filled with ultrapure water, waiting to catch a single proton falling apart. Nothing yet. Current limits put the proton's half-life above 10 to the 29 years. But some grand unified theories predict protons eventually decay. Half-lives around 10 to the 32 or 10 to the 36 years. If true, wait long enough and every proton in the universe transforms into lighter particles. Electrons. Positrons. Neutrinos. Photons. What does that mean for matter? Everything disintegrates. Not through chemical reactions or nuclear fission. Through fundamental particle decay. Planets crumble to photons. Dead stars dissolve. Even neutron stars, the densest stable objects in the cosmos, evaporate as their constituent neutrons decay into radiation. This happens around 10 to the 40 years from now. Every atom gone. Every molecule. Every crystal lattice. All ordinary matter converted to massless particles spreading through an ever-expanding void. If protons don't decay, matter still doesn't last forever. Quantum tunneling provides another route to destruction. On timescales of 10 to the 10 to the 76 years, quantum processes can rearrange matter in bizarre ways. Iron stars, hypothetical objects formed when stellar remnants cool and heavy elements decay to iron through fission, could quantum tunnel into neutron stars. Or into black holes. The calculations stretch probability to absurd limits, but given infinite time, even the impossible becomes inevitable. Quantum tunneling might convert large objects directly into black holes. Not through gravitational collapse, but through quantum probability. The particles constituting a dead star spontaneously rearrange into a configuration dense enough to form an event horizon. Once that happens, the black hole immediately evaporates through Hawking radiation because objects formed this way would be small, and small black holes evaporate quickly. This brings us to the black hole era. After ordinary matter decays or tunnels away, black holes remain. They're the most stable structures in the universe. Nothing escapes. Nothing decays. They just sit there, warping spacetime around them. Except they don't sit there forever. Hawking radiation slowly drains their mass. Stephen Hawking showed in 1974 that black holes aren't entirely black. Quantum effects near the event horizon allow them to emit particles, losing mass in the process. The radiation is real, though we've never detected it directly. the temperature of Hawking radiation is inversely proportional to the black hole's mass. Supermassive black holes, billions of solar masses, radiate at temperatures just above absolute zero. Microscopic black holes, if they existed, would be scorching hot. As a black hole radiates, it shrinks. As it shrinks, its temperature increases. The process accelerates. In the final moments, a black hole evaporates in an explosive burst of high-energy particles. How long does this take? A solar mass black hole evaporates in about 2 × 10⁻64 years. Already unfathomable. Supermassive black holes take much longer. The lifetime scales with the cube of the mass. A black hole with 1 billion solar masses lasts about 2 × 10⁻93 years. The largest black holes, potentially 100 trillion solar masses, persist until 10⁻110 years. After they're gone, what's left? Almost nothing. Photons, electrons, neutrinos. Particles so widely separated by expansion that they almost never interact. The universe enters the dark era, a phase lasting far longer than everything preceding it. In the dark era, the universe is essentially empty. The average distance between particles exceeds the size of the current observable universe. Temperature approaches but never quite reaches absolute zero, asymptoting to a value determined by the cosmological constant. Roughly 10⁻⁻30 Kelvin. Cold enough that nothing happens. No chemistry. No nuclear reactions. No structure formation. The cosmological horizon emits Hawking radiation too. Just like a black hole's event horizon, the universe's cosmological horizon has a temperature. It radiates. Given enough time, even massive objects like neutron stars could be ionized by this radiation, slowly dissipating into their constituent particles. But here's the truly unsettling part. The dark era doesn't end. It just continues. Forever. Expansion never stops. Particles drift farther apart. Interactions become rarer, approaching but never reaching zero. The universe doesn't freeze into stasis. It remains dynamic, technically. Particles still move. Quantum fields still fluctuate. But nothing meaningful happens. No change that matters. No processes capable of generating complexity or consciousness or anything resembling what we'd call events. This is heat death. Maximum entropy. Perfect thermal equilibrium. The second law of thermodynamics fulfilled completely. Energy still exists, evenly distributed, no gradients remaining to drive any work. The universe becomes a static heat bath, unchanging across timescales that make its current age look like a Planck time. You might wonder about quantum fluctuations. Can't they create something from nothing? In principle, yes. Given infinite time, quantum mechanics allows for extraordinarily unlikely events. A random fluctuation could spontaneously assemble particles into complex structures. Even conscious entities. These are called Boltzmann brains, named after Ludwig Boltzmann, who considered such possibilities. The probability is so low it's almost meaningless. Waiting for a Boltzmann brain to randomly form takes timescales like 10⁻10⁻56 years. Numbers so large they lose meaning. By comparison, the evaporation of the largest black holes happens in 10⁻110 years. We're talking about time periods exponentially longer than that. And even if Boltzmann brains appear, what then? They'd exist in isolation, surrounded by void, with no context, no environment, experiencing random memories that never actually happened before dissolving back into particles. It's existence, technically, but not life as we understand it. Not meaning. Just brief statistical flukes in an otherwise dead cosmos. The Big Freeze represents maximum entropy, but entropy itself deserves deeper examination. What does it really mean for the universe to reach maximum disorder? Entropy measures disorder, but that definition oversimplifies. Think of it as the number of possible arrangements a system can have while looking the same macroscopically. A gas in a box has countless ways its molecules can be positioned while still appearing uniform. That's high entropy. Concentrate all those molecules in one corner. Fewer arrangements. Lower entropy. The second law says isolated systems always move toward states with more possible arrangements. Not because nature prefers chaos, but because there are simply more ways to be disordered than ordered. Consider a deck of cards. Shuffle it once. The specific order you get is astronomically unlikely, but it's just as probable as any other specific sequence. What makes it seem random is that we categorize orders. A sorted deck is one specific arrangement we recognize. Every other configuration looks unsorted to us, even though each is equally improbable. There are vastly more unsorted arrangements than sorted ones. Entropy counts those possibilities. Shuffle long enough, you'll almost never return to sorted. Not impossible, just overwhelmingly unlikely. The universe operates similarly. High entropy states vastly outnumber low entropy ones. The Big Bang started the cosmos in an extraordinarily low entropy configuration. Everything since has been entropy increasing, exploring the immense space of more probable arrangements. Stars form, burn, die. Galaxies evolve. Black holes grow and evaporate. Each process moves toward configurations with more microscopic possibilities. Heat death is simply when the universe has explored essentially all available arrangements. Nothing left to shuffle toward. But here's what troubles physicists. Why did the universe start with such low entropy? The Big Bang's initial state was incredibly ordered, incredibly improbable. We don't know why. Some theories suggest our observable universe is a tiny low-entropy pocket in a vastly larger multiverse at equilibrium. A statistical fluctuation. Others propose the initial conditions were determined by physics we don't yet understand. No satisfying answer exists. This connects to the arrow of time. Why does time flow forward? Why do we remember the past but not the future? Physics equations work equally well running backward. Yet we experience time moving in one direction only. The answer relates to entropy. We perceive time's arrow pointing toward increasing entropy. Eggs break, never spontaneously reassemble. Memories form because our brains move from lower to higher entropy states. Reverse the entropy gradient, time appears to run backward. Heat death eliminates that gradient. Does time's arrow disappear? Not exactly. Time likely continues existing as a dimension. But without entropy changes, without events distinguishing past from future, time becomes meaningless from an experiential standpoint. The universe still has temporal extent. Particles still have positions at different times. But nothing happens. No cause and effect. No change to mark time's passage. It's not that time stops, but that it becomes indistinguishable from space in its lack of meaningful variation. This raises philosophical questions physics can't fully address. Is a universe without change truly a universe? Does existence require events? The mathematics suggests yes, the cosmos persists. But in what sense does it exist if nothing can ever observe or experience it? We're venturing beyond science into metaphysics here. Physics describes what happens, not what it means. Return to concrete physics. The Big Freeze assumes dark energy remains constant. That assumption might be wrong. Dark energy makes up 68% of the universe's total energy budget. We don't know what it is. Current observations suggest it behaves like a cosmological constant, Einstein's famous addition to his field equations. He called it his greatest blunder after Hubble discovered cosmic expansion. Turns out he might have been right initially. Maybe. The cosmological constant represents energy inherent to space itself. Vacuum energy. Every cubic meter of empty space contains a tiny amount of energy that creates repulsive gravity, driving accelerated expansion. Measure dark energy's strength over time, it appears constant. But our measurements span only a fraction of cosmic history. We've observed back to when the universe was a quarter its current age. Dark energy dominated for only the last half of cosmic time. Before that, matter's gravity was stronger. What if dark energy changes? Recent data from the Dark Energy Spectroscopic Instrument hints that dark energy might not be constant. The evidence isn't conclusive, but it suggests dark energy was stronger in the past than now. If dark energy weakens over time, the universe's fate changes dramatically. Expansion could slow. Eventually stop. Reverse. This scenario is called the Big Crunch. Imagine a film of the Big Bang running backward. Galaxies start approaching each other. Slowly at first, then faster. Clusters merge. The cosmic microwave background, currently at 3 Kelvin, begins warming. As space contracts, radiation blue shifts to higher energies. The universe heats up. Give it enough time, galaxies collide. Stars merge. Gas clouds compress, triggering massive star formation. But these stars don't last. The universe becomes too hot, too dense. Eventually, the cosmos resembles the early Big Bang in reverse. Matter and radiation reach extreme densities and temperatures. The fabric of spacetime itself curves toward a singularity. Everything that ever was, compressed to a point. The Big Crunch completes. Current observations strongly disfavor this outcome. The universe appears flat geometrically, meaning its density equals the critical value separating eternal expansion from eventual collapse. Dark energy provides more than enough repulsion to ensure expansion continues. Unless dark energy weakens significantly or reverses, the Big Crunch won't happen. But cosmology has surprised us before. Some models propose cyclic cosmologies. The Big Crunch isn't the end but transitions into a new Big Bang. The universe bounces, beginning a fresh expansion phase. Repeat indefinitely. Each cycle could last trillions of years. Roger Penrose developed a version called conformal cyclic cosmology. His model suggests that when the universe reaches maximum entropy, the distinction between a very large old universe and a very small young universe becomes mathematically equivalent. The heat death of one aeon becomes the Big Bang of the next. Penrose's idea is elegant but faces challenges. The second law of thermodynamics creates problems. Entropy increases each cycle. Unless some mechanism resets entropy at each bounce, it accumulates. Eventually, you reach maximum entropy and cycles can't continue. Penrose proposes that massless particles at heat death lose any sense of scale, allowing a conformal transformation to a new beginning. It's speculative. Testable predictions exist, but confirmation remains elusive. There's another possibility, more violent. The Big Rip. If dark energy doesn't remain constant but strengthens over time, expansion accelerates faster and faster. Eventually, the expansion rate becomes so extreme it overcomes all forces holding structures together. Gravity binds galaxy clusters. Those get torn apart first. Then individual galaxies dissolve. Solar systems next. Planets rip from their stars. Eventually, expansion overwhelms electromagnetic forces. Molecules break apart. Atoms disintegrate. Even atomic nuclei get shredded. The strong nuclear force, strongest in nature, finally succumbs. Quarks separate. Spacetime itself tears. This requires a specific type of dark energy called phantom energy, where its density increases as the universe expands rather than remaining constant. Current observations don't support this. Dark energy appears consistent with a cosmological constant. But we can't rule it out completely. If phantom energy exists, the Big Rip could occur in as little as 22 billion years. That sounds distant, but it's cosmologically soon. The universe is already 14 billion years old. We'd be living in the final third of cosmic history. The Big Rip represents a fascinating counterpoint to heat death. Instead of gradually fading into cold darkness, the universe ends catastrophically, torn apart by its own expansion. Which fate awaits depends entirely on dark energy's nature. Something we still don't understand. What is dark energy? Vacuum energy seems likely, but vacuum energy calculations produce predictions wrong by 120 orders of magnitude. That's the worst prediction in physics history. The measured value is so much smaller than theory suggests, we don't know how to reconcile them. Something fundamental is missing from our understanding. Modified gravity theories propose alternatives. Maybe dark energy isn't a substance but a sign that general relativity needs revision at cosmological scales. Some models suggest acceleration arises naturally from spacetime geometry without requiring mysterious energy. These theories remain speculative but active areas of research. Future observations will constrain possibilities. NASA's Nancy Grace Roman Space Telescope launches soon, designed specifically to investigate dark energy's properties and evolution. The Vera C. Rubin Observatory will map the universe's large-scale structure with unprecedented precision. These instruments should determine whether dark energy truly is constant or varies over time. That determination decides the universe's ultimate fate. Constant dark energy means big freeze. Strengthening dark energy leads to Big Rip. Weakening dark energy allows Big Crunch. We're living in an era where we can actually measure which ending our cosmos faces. That's remarkable. For most of human history, the universe's fate was pure speculation. Now it's observational science. Whatever the answer, one thing seems certain. The universe as we know it is temporary. Temporary doesn't mean tomorrow. The timescales involved stretch beyond human comprehension. Let's walk through what actually happens, step by step, as the universe marches toward its end. First, the near future. Relatively speaking, Our Sun has roughly 5 billion years remaining. It's currently halfway through its main sequence lifetime, steadily fusing hydrogen into helium. When that hydrogen runs out, the core contracts. Temperature rises. Hydrogen fusion begins in a shell around the core. The Sun swells into a red giant, expanding outward. Mercury gets swallowed. Venus follows. Earth might survive, might not. Depends on mass loss and tidal effects. Either way, temperatures on Earth become incompatible with life long before potential engulfment. Oceans boil away. Atmosphere strips off. The Sun then sheds its outer layers, creating a planetary nebula. The core remains as a white dwarf, slowly cooling over billions of years. That's just one star. Across the universe, star formation continues. But not forever. Star formation requires gas. Specifically, cold molecular hydrogen. As stars form, they consume this gas. Some returns to the interstellar medium when stars die, but not all. Heavy elements build up. Efficiency drops. Models predict star formation peaks already passed. The universe reached maximum stellar brightness billions of years ago. Now it's fading. In about 100 trillion years, give or take, star formation effectively ceases. The last stars ignite. Red dwarfs dominate at this point. They burn slowly, efficiently. A red dwarf with mass around 8% solar can last 10 trillion years or more. They're the ultimate survivors, extracting every possible joule from their fuel. But eventually, they too exhaust their hydrogen. They contract into white dwarfs. No supernova. Just gradual dimming. This marks the end of the stelliferous era. The age of stars. What follows is the degenerate era, named for the degenerate matter composing white dwarfs, neutron stars, and black dwarfs. Black dwarfs don't exist yet. They're theoretical. White dwarfs that have cooled completely, radiating away all thermal energy. That takes longer than the current age of the universe. Much longer. But eventually, white dwarfs fade to black. During this era, galaxies still exist structurally. Stars are dead, but gravity keeps them bound. However, gravitational interactions slowly eject stars from galaxies. Close encounters between stellar remnants provide energy for one object to escape, the other falling deeper into the gravitational well. Over quadrillions of years, most stellar remnants get ejected into intergalactic space. Those remaining fall toward the supermassive black hole at the galactic center. Galaxy becomes black hole plus scattered remnants. Speaking of black holes, they grow during this period. They merge when galaxies collide. They accrete remaining matter. Supermassive black holes at galaxy centers consume nearby stellar remnants. Some models suggest these could reach masses of 100 trillion suns. But growth eventually stops. Expansion carries matter away faster than black holes can capture it. Isolation sets in. Then comes something truly strange. Proton decay. Maybe. Grand unified theories predict protons aren't stable. They should decay, eventually, into lighter particles. Experiments haven't detected this yet. Current limits put proton half-life above about 10 to the 29th years. But theoretical predictions suggest decay between 10 to the 31st and 10 to the 36th years. If protons decay, the implications are staggering. Everything made of protons and neutrons disintegrates. Stellar remnants, planets, dust, everything. A white dwarf is mostly carbon and oxygen nuclei. Those nuclei contain protons. When protons decay, the white dwarf dissolves into radiation and lighter particles. Same for neutron stars, despite the name. They contain protons in their crusts and possibly their cores. Those decay too. This happens slowly. Half-life of 10 to the 34th years means after that time, half the protons have decayed. After twice that, 3/4 gone. After 10 half-lives, over 99% vanished. But it's gradual. A white dwarf wouldn't explode. It would slowly evaporate, particle by particle, over incomprehensible time. What remains? Photons, electrons, positrons, neutrinos, black holes. Electrons and positrons don't decay, as far as we know. They're fundamental particles. Same with photons and neutrinos. These become the universe's primary constituents. Plus black holes. Black holes now enter their final act. Hawking radiation. Quantum effects near the event horizon allow black holes to emit particles. The process is incredibly slow. A black hole radiates like a blackbody with temperature inversely proportional to its mass. Larger black holes are colder. A solar mass black hole has temperature around 10 to the -7th Kelvin. Colder than the cosmic microwave background. So currently, black holes absorb more radiation than they emit. They grow. But the cosmic microwave background cools as the universe expands. Eventually, it drops below the black hole's temperature. Then Hawking radiation dominates. The black hole loses mass. As mass decreases, temperature increases. Radiation intensifies. The process accelerates. For a solar mass black hole, complete evaporation takes about 10 to the 64th years. For a supermassive black hole of 1 billion solar masses, roughly 10 to the 91st years. Those hypothetical 100 trillion solar mass black holes last until about 10 to the 109th years. These numbers are almost meaningless. They're so large that intuition fails completely. Yet even these timescales are nothing compared to what follows. After the last black hole evaporates, the universe enters the dark era. Only photons, electrons, positrons, and neutrinos remain. They're spread incredibly thin. Expansion has diluted everything. The average distance between particles exceeds the size of the current observable universe. Encounters become vanishingly rare. Thermodynamically, the universe approaches maximum entropy. Energy distributes uniformly. Temperature gradients disappear. No work can be performed. This is heat death. Not cold, exactly. A very low but non-zero temperature. Around 10 to the -30 Kelvin, determined by the cosmological constant. But uniform. No differences. No flows. No structure. Does anything happen in the dark era? Technically, yes. Quantum mechanics never stops. Virtual particles fluctuate in and out of existence. Occasionally, real particles might form from quantum tunneling. The probabilities are astronomically small, but time is infinite. Or effectively so. This leads to Boltzmann brains. Random fluctuations could, in principle, assemble conscious entities. Not through evolution or design. Pure chance. Given enough time, any configuration allowed by physics eventually appears. Including brains. With memories. Experiences. Completely spontaneous. The timescale for such events: 10 to the 10 to the 50 years. Maybe 10 to the 10 to the 70. Numbers so large we can't write them in standard notation. The exponent has an exponent. These durations make the black hole era look instantaneous. Boltzmann himself found this deeply troubling. If fluctuations can produce brains, why don't we see evidence of living in a fluctuated universe? Statistical mechanics suggests we're more likely to be random fluctuations than products of a structured cosmos. The fact that we observe order implies we're not fluctuations. Probably. This remains philosophically unsettling. There's another possibility. Quantum tunneling could reset everything. In principle, quantum mechanics allows transitions between vacuum states. Our universe might exist in a false vacuum, metastable but not permanent. Tunneling to a true vacuum would release enormous energy, potentially creating a new Big Bang. The probability is unimaginably small. But infinity is long. Estimates suggest such an event might occur around 10 to the 10 to the 10 to the 56 years. That's 10 to the power of 10 to the power of 10 to the power of 56. Writing it out is impossible. The number of particles in the observable universe is only about 10 to the 80. This timescale dwarfs everything. Would we call that a new universe? Depends on your definition. The laws of physics might differ. Constants could change. It wouldn't be our universe continuing. More like a completely fresh start. But here's the thing. All these far future scenarios assume current physics holds. We're extrapolating laws discovered in the last few centuries across timescales trillions of times longer than those laws have been tested. That's optimistic. Maybe even naive. Physics could change. New phenomena might emerge at extreme energies or durations we haven't accessed. Undiscovered particles, forces, or principles could dominate the far future. We're like someone in the 19th century predicting technology in the year 3000. Based on steam engines and telegraphs. They'd miss nuclear power, semiconductors, quantum computing, everything fundamental to the actual future. Our predictions about the universe's end rest on similar assumptions. We know the second law of thermodynamics works now. Does it work forever? We've never tested it over 10 to the 100 years. Maybe something breaks down. Maybe entropy has limits we haven't discovered. Maybe the universe has mechanisms for renewal we can't imagine. That doesn't mean heat death is wrong. Best evidence supports it. But certainty is unwarranted. We're extrapolating wildly beyond our data. The honest answer to how the universe ends is, we don't know for sure. We have models. Good models, based on solid physics. But models aren't reality. They're approximations. And even if heat death is correct, even if the universe fades into cold, dark uniformity, that raises a question. What does ending even mean when time continues? Heat death describes a state where time exists but nothing happens. Clocks could theoretically tick. Particles could move. But no events of significance occur. Temperature becomes uniform everywhere. Energy spreads evenly. And when energy distributes perfectly, no work can be done. No reactions. No processes. No change. The universe becomes a static tableau. Frozen not by cold, but by equilibrium. This contradicts our intuition about endings. We imagine finales as dramatic moments. Explosions. Collapses. Definitive stops. Heat death offers none of that. Just continuation without meaning. Time marching forward while nothing meaningful transpires. It's the difference between a movie ending and a movie that simply stops advancing the plot while the camera keeps rolling. Forever. That's arguably more disturbing than annihilation. But let's consider an alternative. What if dark energy isn't constant? Recent observations from instruments like the Dark Energy Spectroscopic Instrument suggest dark energy's strength may vary over time. It might have been stronger in the past. Weaker now. If that pattern continues, if dark energy keeps weakening, expansion could slow. Eventually stop. Then reverse. Leading to the Big Crunch. Galaxies would begin moving toward each other instead of apart. Initially, the change would be imperceptible. Distant galaxies would stop receding. Then slowly approach. Over billions of years, clusters would merge. The cosmic microwave background would shift from red to blue as radiation compressed. Temperatures would rise. Not everywhere at once, but gradually, systematically. As space contracted, everything would heat up. The Big Crunch inverts the Big Bang. Instead of starting from infinite density and expanding, the universe collapses back toward infinite density. Stars would collide. Planets would vaporize. Black holes would merge into larger ones. Temperature would climb past the point where atoms exist. Then past where nuclei survive. Eventually, even quarks would dissolve into pure energy. Everything crushed into a singularity. A point of infinite density and temperature where physics breaks down. Where our equations produce infinities and stop making predictions. Would that be the absolute end? Or could something emerge from that singularity? Perhaps another Big Bang. A cyclic universe, endlessly repeating. Birth, expansion, contraction, death, rebirth. Over and over. Cyclic models have appeal. They avoid the uncomfortable question of ultimate origins. If the universe cycles eternally, there's no beginning to explain. No first cause. Just an infinite chain. But thermodynamics creates problems. The second law states entropy always increases. Each cycle would start with more disorder than the previous one. Eventually, entropy would max out. The cycle would stop. Unless some mechanism resets entropy. Roger Penrose proposed one idea. His conformal cyclic cosmology suggests that at maximum entropy, when all massive particles have decayed, the universe becomes mathematically equivalent to a new beginning. The distinction between infinitely old and infinitely large versus infinitely young and infinitely small blurs. The end of one aeon becomes the start of another. It's elegant. Speculative. Unproven. But it offers a way around the entropy problem. Then there's the Big Rip. If dark energy strengthens instead of weakening, expansion accelerates faster and faster. Eventually, the repulsive force of dark energy overpowers everything else. First, galaxy clusters tear apart. Then individual galaxies. Then solar systems. Eventually, molecular bonds break. Atoms split. Even subatomic particles rip apart. Spacetime itself shreds. This would happen relatively quickly, cosmologically speaking. Perhaps 20 billion years from now. Some calculations suggest 22 billion. The Big Rip doesn't require infinite time. Just dark energy that grows stronger. Current observations don't support this. Phantom energy, the type needed for a Big Rip, hasn't been detected. But we can't rule it out completely. Each scenario depends on dark energy's behavior. And we don't understand dark energy. It constitutes 68% of the universe's total energy. Dominates cosmic evolution. Yet we can't explain what it is. Some theories suggest it's vacuum energy, a fundamental property of empty space. Einstein's cosmological constant, which he called his biggest blunder, might actually describe reality. Others propose modifications to gravity itself. Maybe general relativity needs adjustment at cosmic scales. Maybe acceleration emerges from space-time geometry rather than mysterious energy. These ideas remain speculative. We're gathering data. Missions like the Nancy Grace Roman Space Telescope, launching in 2027, will map dark matter and track dark energy's evolution. But answers won't come quickly. What's certain is this: the universe is dying. Not today. Not tomorrow. But the process has begun. Star formation peaked billions of years ago. We're already in the decline phase. Galaxies are making fewer stars now than they did in the past. Gas supplies are depleting. The universe is slowly fading. In 100 million years, we won't be able to observe galaxies outside our local group. Expansion will carry them beyond our cosmic horizon. They'll still exist, but we'll never see them. Their light will never reach us. Our observable universe will shrink. Not because space is contracting, but because expansion is accelerating. Eventually, only our local cluster remains visible. Then just our galaxy. Then nothing beyond our solar system. Assuming our solar system still exists. It won't. 5 billion years from now, the Sun enters its red giant phase. It expands dramatically. Engulfs Mercury. Probably Venus. Possibly Earth. The Sun's outer layers reach toward Mars. Our planet either vaporizes in the stellar atmosphere or becomes a charred cinder orbiting a dying star. The outer planets survive. For a while. But they'll drift into darkness as the Sun fades to a white dwarf. Then a black dwarf. Then, if protons decay, even those remnants dissolve. Our entire solar system, everything humanity has ever known, will vanish completely. Not in some distant theoretical future. In 5 billion years. That's soon. Cosmologically. By the time the last stars die, by the time black holes evaporate, by the time the universe reaches heat death, Earth will have been gone for trillions of years. Humanity, if it still exists in any form, will have migrated elsewhere, or evolved beyond recognition, or gone extinct. Our planet is a temporary home. Our sun is a temporary star. Everything we see is temporary. That's not pessimism. It's thermodynamics. The second law doesn't care about our feelings. Entropy increases. Order becomes disorder. Structure dissolves. And ultimately, everything equalizes. Does this mean nothing matters? That's a philosophical question, not a scientific one. Physics describes what will happen. It doesn't prescribe meaning. You could argue that temporary things matter more because they're rare. A universe at heat death has infinite time but no events. We live in a brief window where events occur. Stars shine. Life exists. Complexity emerges. That's extraordinary. The fact that it ends doesn't diminish its value while it lasts. A sunset doesn't become less beautiful because it fades. If anything, the impermanence intensifies the experience. Or you could take the opposite view. If everything ends in maximum entropy, if all complexity dissolves, then perhaps nothing we do has lasting significance. Our greatest achievements, our deepest thoughts, our most profound discoveries, all eventually forgotten. Not just forgotten by people. Forgotten by the universe itself. When the last black hole evaporates, when the last photon redshifts into nothingness, every trace of human existence will be gone. We'll leave no mark. The cosmos will continue, empty and cold, with no memory that we ever existed. That's humbling. Maybe crushing. But again, this assumes current physics holds forever. We're extrapolating laws tested over hundreds of years across timescales of 10 to the 100 years. That's absurd when you think about it. We've observed the universe for a tiny fraction of its lifetime. We've conducted experiments for an even tinier fraction. And from that limited sample, we're making predictions about the infinite future. It's like watching the first second of a movie and claiming to know how it ends. We might be right. We might be completely wrong. New physics could emerge. Undiscovered particles. Unknown forces. Phenomena that only manifest over trillion-year timescales. We have no way of knowing. String theory suggests extra dimensions we can't access. Quantum mechanics implies realities we can't observe. Dark matter interacts gravitationally but remains invisible. Dark energy drives expansion but defies explanation. Our understanding of the universe is incomplete. Dramatically incomplete. We know roughly 5% of what exists. The other 95%? Mystery. We've labeled it dark matter and dark energy. But labels aren't understanding. We're describing our ignorance, not explaining reality. Given that, confident predictions about the universe's ultimate fate seem premature. Still, we work with what we have. Heat death remains the leading scenario. Best fit to current observations. But science is provisional. Always subject to revision. New data could overturn everything tomorrow. That's happened before. Einstein overturned Newton. Quantum mechanics shattered classical certainty. The discovery of accelerating expansion upended cosmology. Each revolution revealed how much we didn't know. The next one will do the same. Maybe the universe doesn't end. Maybe it transforms. Maybe our concept of ending is too limited. Maybe time itself is temporary, and asking what happens after time stops is meaningless. We don't know. Can't know. Not yet. What we do know is this: the universe won't end soon. Not in any human time frame. Not in any time frame relevant to biological life. Stars will shine for trillions of years. Galaxies will persist for quadrillions. Black holes will dominate for incomprehensible durations beyond that. And even if heat death is correct, even if the universe fades to uniformity, that happens on timescales that make geological ages look instantaneous. For all practical purposes, for everything we care about, the universe is eternal. Our sun will die. Our galaxy will change. But the cosmos will continue. And in that continuation, perhaps something emerges we can't imagine. Perhaps consciousness finds a way to persist. Perhaps life adapts to energy-poor environments. Perhaps intelligence transcends physical form entirely. Or perhaps not. Perhaps heat death is inevitable and final. Perhaps the universe really does end in cold, dark silence. We'll find out. Eventually. In the meantime, we exist in the most interesting era possible. When stars burn. When complexity thrives. When questions like these can be asked. That window is narrow. But it's open now. And we're here to witness it. We exist at a specific moment in cosmic time. Not the beginning. Not the end. Somewhere in the middle of a story we can't fully read. The universe is roughly 14 billion years old. It might last forever, in some sense. Or it might end violently in 22 billion years. Or fade slowly over googles of years. The uncertainty isn't a failure of science. It's the current state of knowledge. We're doing cosmology with limited data, making predictions that extend far beyond our ability to verify. Think about what we're attempting. Humans have existed for maybe 300,000 years. Civilization for 10,000. Modern physics for 400. Cosmology as a rigorous science for less than a century. We discovered dark energy in 1998. 25 years ago. And from this brief window of observation, we're projecting forward to the heat death of everything. The audacity is remarkable. Also necessary. Science works by making predictions, testing them, refining models. We can't test predictions about 10 to the 100 years from now. But we can test whether our models correctly describe the universe's past. They do, mostly. General relativity works. Quantum mechanics works. Thermodynamics works. So we extend them forward, cautiously, knowing we might be wrong. The scenarios we've explored aren't fantasies. They're serious attempts to understand physical law's ultimate consequences. Heat death follows directly from thermodynamics. The Big Rip emerges from certain dark energy models. The Big Crunch requires specific cosmic geometry. Cyclic universes attempt to reconcile expansion with eternal existence. Each represents a genuine possibility given current physics. But current physics isn't final physics. It's physics as we understand it now. Tomorrow's discoveries might change everything. What matters most isn't which ending awaits. It's that we can ask the question scientifically. For most of human history, the universe's fate was theology or philosophy. Now it's observational science. We measure cosmic expansion. We track supernovae. We map dark matter. We calculate entropy. The answers might be disturbing. They might be incomplete. But they're grounded in evidence, not speculation. That's progress. Real progress. And here's something worth considering. The universe's eventual death doesn't negate everything in between. A song doesn't become meaningless because it ends. A story doesn't lose value because you finish reading it. If anything, finitude creates significance. Infinite time makes each moment worthless. Finite time makes each moment precious. Even if that finite time spans trillions of years, it's still bounded. Stars will burn out. We should appreciate them while they shine. The same applies to consciousness. If the universe reaches heat death, if all complexity dissolves, then conscious experience becomes a temporary phenomenon. A brief window in cosmic history when matter organized itself into thinking beings. That window might last billions of years. Might span countless civilizations. But it's finite. Eventually, the conditions supporting consciousness disappear. Does that make consciousness less significant? Or more? You decide. Physics can't answer that. What physics can tell you is that we live in an extraordinary time. Not just for humanity, but for the universe itself. The stelliferous era, the age of stars, represents a tiny fraction of cosmic history. Most of the universe's past was too hot for stars. Most of its future will be too cold. We exist during the brief interval when stellar fusion is possible. When galaxies shine. When complexity emerges naturally from gravitational collapse and nuclear reactions. This era is special. Objectively, mathematically special. And we're here to observe it. Conscious minds capable of understanding thermodynamics, general relativity, quantum mechanics. Capable of asking how the universe ends and actually formulating answers. That's astonishing. The universe has become aware of itself through us. It's using our brains to contemplate its own mortality. When you think about heat death, you're engaging in the cosmos examining its eventual fate. The atoms in your brain, forged in stellar cores, are considering the death of stars. Carbon pondering entropy. Hydrogen contemplating heat death. This self-awareness won't last forever. Consciousness might be common in the universe, might be rare, might be unique to Earth. We don't know. But wherever it exists, it's temporary. The conditions supporting life are narrow. Temperature must be moderate. Stable energy sources must exist. Chemistry must be complex enough. These conditions exist now. They won't always. Eventually, the universe becomes too cold, too dispersed, too uniform to support any form of complexity, including consciousness. The cosmos will continue existing, but it won't be aware of itself anymore. The brief flicker of self-reflection will have passed. Unless something changes. Unless physics we haven't discovered allows for consciousness in low-energy environments. Unless life finds ways to persist we can't imagine. Unless the universe itself has properties we've completely missed. Those are genuine possibilities. We've been wrong before. spectacularly wrong. Scientists once thought space was filled with luminiferous ether. That time was absolute. That the universe was static. Each assumption seemed obvious, well supported, nearly certain. Each turned out to be completely incorrect. Our current understanding of cosmology might be similarly flawed. We think dark energy drives acceleration. We think protons might decay. We think heat death awaits. But we thought lots of things that weren't true. The honest position is uncertainty. We have good models, strong evidence, reasonable confidence, but not certainty. Never certainty. The universe doesn't owe us comprehensibility. It might operate on principles we can't access, following rules we can't discover. Or it might be exactly as it appears, governed by laws we've already identified, heading toward exactly the fate thermodynamics predicts. Both possibilities remain open. What we do with that uncertainty defines us. We could despair. Knowing everything ends, why continue? Why build civilizations? Why create art? Why seek knowledge? If heat death erases everything, what's the point? That's one response. Valid, maybe. But not the only one. Another response is curiosity. We might not affect the universe's ultimate fate, but we can understand it. That understanding is its own reward. Figuring out how reality works, even if reality ends badly, satisfies something deep in human nature. We want to know. Need to know. The answer doesn't have to be comforting to be valuable. And there's a third response. Defiance. The universe might be dying, but it's not dead yet. Entropy might win eventually, but not today. Not for trillions of years. In the meantime, we can create, build, think, experience, love, laugh, discover. All temporary, yes. All ultimately erased by heat death or the Big Rip or whatever awaits. But real while they last. The universe gives us this brief window of low entropy, this temporary pocket of order in an ocean of chaos, and we can either appreciate it or waste it mourning its inevitable end. Consider Earth. Our planet formed 4.5 billion years ago. It'll be destroyed in 5 billion years when the sun expands. That's 9.5 billion years total. We've existed for 300,000. That's 0.003% of Earth's lifetime. A rounding error. And yet, in that fraction of a percent, we've developed language, mathematics, science, art, music, philosophy. We've sent machines to other planets. Looked back at distant galaxies. Calculated the universe's age and predicted its death. That's not bad for 0.003%. Imagine what could happen in the remaining time. 5 billion years is a long time. Longer than life has existed on Earth. If humanity survives, if intelligence persists, what might we accomplish? We might spread to other stars. Outlive Earth's destruction. Witness the sun's death from safe distance. We might learn to harness energy more efficiently, survive longer as stars dim. We might discover new physics that changes everything. Or we might go extinct next century. Destroy ourselves through war or environmental collapse or simple carelessness. both outcomes remain possible. Neither is predetermined. But here's what's certain. Right now, in this moment, we exist. You're reading these words, thinking about the universe's fate. That's real. That's happening. The heat death is theoretical, trillions of years away, maybe not even correct. Your consciousness is actual, present, undeniable. The universe might end in darkness, but it's not dark now. Stars are shining. Galaxies are forming. Life is persisting. And you're part of that. A tiny part, yes. But a part nonetheless. The universe doesn't care about you. It's not hostile. It's indifferent. Physics operates without regard for human concerns. Entropy increases whether we like it or not. Stars die on their own schedule. Heat death approaches at its own pace. None of it considers our feelings. That's uncomfortable. We want meaning. We want purpose. We want the cosmos to acknowledge our existence. It doesn't. It can't. It's not conscious, except through us. So we create our own meaning. We decide what matters. The universe provides the stage, the props, the physical laws. We write the play. And our play includes asking how the universe ends, contemplating heat death, calculating black hole evaporation times, measuring dark energy. These activities don't change the outcome. The universe will end however it ends, regardless of whether we understand it. But understanding is valuable anyway. Not because it prevents heat death, but because understanding is what we do. It's how we respond to existence. We observe. We question. We calculate. We predict. And sometimes our predictions are wrong. Sometimes reality surprises us. The universe is under no obligation to make sense. But it does, mostly. The fact that mathematics describes physics, that experiments produce consistent results, that observations match predictions, that's not guaranteed. It's extraordinary. We live in a universe that's comprehensible. At least partially. At least to the extent we've tested. That might not last forever. New phenomena might be incomprehensible. Or we might understand everything eventually. We don't know. What we know is that right now, the universe can be studied. And we're doing it. With telescopes and particle accelerators and mathematical models. With observations of distant supernovae and measurements of cosmic expansion. With calculations of entropy and predictions of heat death. We're mapping the future. Or trying to. The map might be incomplete. Might be wrong in places. But it's based on the best data we have. The best theories we've developed. The most rigorous thinking we're capable of. And that thinking leads to an uncomfortable conclusion. Everything ends. Not metaphorically. Not eventually. Definitely. The stars will burn out. The galaxies will disperse. The black holes will evaporate. The universe will reach maximum entropy. And when that happens, when heat death completes, nothing will remain but uniform darkness. cold, silent, unchanging, forever. That's what physics predicts. That's where thermodynamics points. That's the most likely fate of everything that exists. You can choose how to respond to that. You can despair. You can deny. You can ignore it entirely. Or you can accept it and continue anyway. Keep asking questions. Keep seeking answers. Keep creating meaning in a universe that offers none inherently. The choice is yours. The universe won't judge. It can't. It's not capable of judgment. It just exists, following its laws, moving toward its end. Indifferent to everything in between. Including you. Including me. Including everyone who's ever lived or ever will live. We're temporary patterns in a universe moving toward uniformity. Brief fluctuations of low entropy in a cosmos trending toward maximum disorder. And when disorder wins, when entropy completes its work, we'll be gone. Completely. Permanently. With no trace remaining. The universe will have forgotten us. Because the universe never knew us in the first place. That's the reality thermodynamics describes. Cold. Mathematical. Inevitable. You can accept it or reject it. But you can't change it. Not with hope. Not with denial. Not with anything. Physics doesn't negotiate. The second law of thermodynamics doesn't make exceptions. Entropy increases. Always. Without fail. Leading ultimately to heat death. Or the Big Rip. Or something else we haven't imagined. But to ending. Definitely to ending. And yet, despite knowing this, despite understanding the universe's fate, we continue. We build. We create. We love. We think. We ask how the universe ends, knowing the answer won't save us. Knowing nothing will save us. And we do it anyway. Because we're here now. Because consciousness exists now. Because in this brief window between the Big Bang and heat death, in this narrow slice of cosmic time when complexity is possible, we have the extraordinary privilege of being aware. Of asking questions. Of seeking answers. Even if those answers are disturbing. Even if they point toward our own inevitable erasure. That's what it means to be human in a dying universe. To know the end is coming. To understand it scientifically. And to keep going anyway. Not because we can change it. But because while we're here, while stars still burn and galaxies still shine, while consciousness still flickers in this cold, indifferent cosmos, we might as well understand it. Might as well appreciate it. Might as well ask how it all ends. Even knowing we won't like the answer.